just be
liquid or and that's the second.
You start just coming to get sure as you move.
Any other questions? Yeah, so the Lofgren state, the plasma being in a split is not a big crystal. Okay, so what we're going to do, we've got 2 lectures this week, and both of them we're just going to describe not Lofgren states. So we're going to start to think about quantum Hall and other filling fractions. In this lecture, we're going to describe how this order of fractions emerges from 2 different perspectives. So we'll see, as systems get cleaner and cleaner, you start to see more and more fractions in a very particular order, and we'll explain why that.
We can start actually.
And then on Friday's lecture, we're going to look at what's actually the most interesting quantum Hall state.
He was not aware of the timing for today.
Oh, okay. Is he on his way? Or?
I think so, actually.
Okay. And so on Friday, we'll look at non-linear. So these are the most interesting states that people propose to use for quantum computing.
Sorry, he forgot.
That's okay.
I think we should go ahead.
Yeah. Well, I should say where we're going. So I was just saying, this lecture and next lecture, we're going to look at fractional quantum Hall states that are not states, other filling fractions. After that, I think there's a break next week. And then if there's an appetite to continue, the next step is to do Chern-Simons theories for about a week, and then after that to do conformal field theories. So if people still want this to continue afterwards, that's all right. So there's one last thing I want to do about Lofgren states, which is again to do with this issue that you were asking. What's a universality? So there's another way to think about a universality. It's also called topological. Okay, so the basic idea is you take your state, your quantum Hall state, and you put it on a manifold which isn't the plane or a sphere, but a 2-dimensional manifold with more topology. And the simplest thing is just put it on a torus. So we'll consider quantum Hall state. Here's the torus. And then we're going to consider the following process. So, what we're going to do is we know that within this quantum Hall state, there are quasi-particle and quasi-Hall excitations. They carry fractional charge and fractional size. So the process we're going to consider is the following. We're going to create somewhere on the torus from the vacuum a particle form. Create particle form there. So this is a particle, and this is a hole. We create those two. And then what we do is we take them and we move them around one cycle of the torus, and then we annihilate them. So we're going to take the blue one and move it around this cycle and annihilate it with.
So the particle presumably has the opposite charge.
Yeah, exactly. So they cannot be annihilated.
Yeah. Okay.
Sorry, the way we defined our hole, it was just some region where particles couldn't be there, right? In the wave function.
Well, it's really the physical excitation of the wave function.
So
these are things that can move around.
Well, I mean, okay, yeah. But the particle was adding one more. Wasn't that adding one more particle? When we talked about
No, it was still adding fractional charge here, minus here.
Okay, but it's the same number, I forgot, sorry, it's the same number of electrons, but just an excited state.
Yeah, that's right, the electrons just get compressed a little bit in that region of extra. Okay, so we move them around the cycle. And then we annihilate them. Okay, so it's a very, very simple process. So this is one thing we can do, and if we do this process where we move them around that cycle, I'm going to call this the operation T1. So T1 is going to be an operator on a Hilbert space that, we'll see exactly what Hilbert space shortly, that acts on the Hilbert space in with something, maybe it's a phase, maybe it's something more complicated, if you do this object. The other thing we can do is create some particles here, and then move one of them around the other cycle twice. And this I'm going to call T2. Okay, so we've got these two different operations. Now, because these are anyons, it depends on the order in which you do this. So doing T1 and then doing T2 is not the same as doing T2 and doing T1. And okay, so let me write down the mathematical statements, and then I'll try to justify it. So the claim is that the operator T1, T2, T1 to the minus 1, T2 to the minus 1, where T1 to the minus 1 is moving them the other way around. Takes one anion around another. So this means that if you were to consider this process, and it's a little hard to visualize topologically, but if you were to consider this process, what you would end up with is one anion moving in a loop and another anion moving in a loop. And the paths defined by this operator have linking number 1. So they can't be separated. Okay? And it's I have to confess, I don't know of a good proof of this. If you stare at it long enough, you can kind of convince yourself that it's probably true. But Preskill has a couple of pages. Preskill has beautiful lecture notes on quantum computing. And there's a chapter called Topological quantum computing where he discusses a lot of this. And he has a couple of pages where he tries to justify that. That's the best I can see.
So just to push T1 is you first create the particle per pair, take it around the cycle, and then annihilate it.
No. Yeah, exactly.
Okay, so you're technically back to your ground state. Well, modulo whatever you get as an addition as you.
Yeah, so what are these operators acting on? You start with a ground state, you do this, you go back to a ground state. So these operators have to be acting on the ground state.
Yeah.
Or ground states, which is actually their way again. So what does this mean mathematically? It means that this takes one anion around another, but we know what happens if you take one anion around another, you pick up a phase. So this means that T1 times T2 2 pi I over n T2 T1. So we have notes. Goodness, right to the notes. Okay, because this is the phase that you pick up from fractional statistics if one anion goes around. So if you buy this, which I don't have a better argument for other than stare at it in the frequency of your own home and convince yourself that it's likely to be true, then this follows. So you have these processes acting on ground states, and these processes have to obey this algebra.
It's like this, when you take, suppose, put some boundary condition and identify, say, some field up to some group element G, right? And it's like G1 along this side and G2 along this side. And then G1 and G2 don't come out.
Yeah, I think that's
It's
exactly
like,
what's happening. Okay? So this is how the operators have to act on the ground state. Now, it's a fact that this algebra can't be realized if T1 and T2 are acting just on a single ground state. Because what can they do? They can only have phases, and this has to be like this. So the smallest representation of this algebra is on a Hilbert space of dimension n, where m sits here as the phase of the n. So the smallest representation of this algebra we're going to identify this as the dimension of the degeneracy of ground states. So this is the number of ground states that you get if you put this system together. It might be more, but this is the minimum number it has to be. So what is the representation? It's very simple to write down the representation on an n-dimensional ordered space. So let me just completely convince you that such a representation exists. So n label the ground states. N is going to go from 1 to n. T1 just multiplies the ground state by a phase. And T2 shifts the ground state by 1. So if you just won't do T1, T2, and then let's see this algebra is obeyed if this is the way it actually makes sense. If you redo this for a manifold with different topologies, so a genus G Riemann circles with lots of holes, it's now clear there's lots of things you can do. Right? You can move them around every cycle within this. So it shouldn't be surprising that on a genus G surface, so G is the number of holes, the ground state degeneracy d to m to the power G.
So the only way you can talk about topological order is putting in on manifolds of different genes. Usually, the original thing that we started with, we can't really talk. Although we see manifestations, we can't cleanly talk about topological order.
I think you can. So firstly, there's the fractional statistics, and it's clear from here that the fractional statistics are very closely related to topology. I think more recently, people in the audience will know better than me, this has been related to entanglement potential. So what's sitting here is called the quantum dimension. Here, obviously, it's an integer. In more interesting systems, it actually turns out to be not an integer. And this is the asymptotic growth as G goes towards infinity. But I know you mentioned the words quantum dimension. I think it's precisely this object there. In this case, and it emerges by doing some entanglement calculation. Is that right? Is that the content of the Prescott?
That's right. Although my own understanding, I know as a calculational factor it's the same number, but in a deep way, why does it have to be? I don't understand that.
Is that understood, or one of those mysteries?
Yeah, I'm not sure. Kita Press will just say, oh, it is the quantum dimension, as if it's obviously true for them, but mere mortals. But just to say one thing, I don't know if there's a map to Chern-Simons theory here.
Absolutely. It's the same as Chern-Simons.
Yeah. If that's the case, we should, just as field theorists, be able to figure out why it is. Although I can't say I've done it.
Well, why this is the same as Chern-Simons theory, or why it's the same as entanglement?
Why the entanglement cares exactly about the anionic statistics as cared, and that in turn cares about.
I see. And we'll see. I think I'll redo this calculation for Chern-Simons theory when we understand how Chern-Simons works. And if you take U1 Chern-Simons and then n, that's the ground state degeneracy.
Because just to say, sorry, Kita Prestel, when they do their calculation of topological entanglement, for the Chern-Simons, they couch it in terms of, Berliner formulas and so on and so forth. And so if we understand how those formulas are tied to the anionic statistics and so on, we should be able to
you can also express this in terms of the anions. There are these fusion rules that came out of more cyber, which are really the defining. If you write down a formal definition of what an anion is, then the fusion rules are the issue.
Okay, I see.
The Berliner formula I don't understand, because the Berliner formula is to do with how S matrix, that's how modular invariant is.
Yeah. And the different, that's right. It could just be that you only need the fusion rules. I'll have to check what's the ingredient. But that might be a route for people like us to connect up.
And I should say, all of that stuff about anions and fusion rules, I learned from Prescott Fletcher. Okay, so what's the basic idea of this? Firstly, And note that it's really striking. You have some system, and all you do is change the topology of the manifold that it's on, and suddenly you're guaranteed to have this absolute degeneracy of ground states. I guess in principle the ground states can be lifted by maybe e to the minus L, where L is the size of the cycle, because that's the probability to tunnel for this process to actually happen in the tunnel. But okay, very, very good bit. Very good approximation. It's absolute ground degeneracy. It's very striking. So the idea is due to when, is the following. That we're used in standard physics to classify phases in terms of symmetries and symmetry breaking patterns and such. This is the Landau gate. And this doesn't work for the fractional quantum world. And there's no local order parameter that tells you whether you're in a fractional quantum Hall phase or what that quantum Hall phase is, even though it's clear that the physics of these phases is radically different. So Wen's idea was that this is one of the things that should replace the old concept, should be added to the old concept of characterizing phases. You shouldn't just characterize phases by symmetry. You should think about what's called topological order, which is the ground state degeneracy. Characterize phase of the state. By the ground state degeneracy. This is the idea of topological. And as we've been saying, this idea is arising in other concepts like entanglement entropy, which suggests that it is a good way to think about the state. It's capturing key information about the phase of this state.
Okay, I can just ask a question. Just because we were talking about Chern-Simons theory, could we still resort to our old ideas of universality classes for Hamiltonians or Lagrangians, just by saying that, okay, maybe all of these theories have a universal description as a Chern-Simons theory, and then the consequences which follow are those from that theory. That's something we would be more familiar with because it's not maybe phases, but we are still writing down the laws of the Hamilton relevant operators consistent with symmetries. And
that's absolutely right. It's the idea that you can have topological operators that don't contribute propagating degrees of freedom, but still change. And that's exactly to respect next week after. Whenever next lecture after this week. In fact, it's worth just advertising that. So the way we'll approach things in 1 week's time is we'll forget about all of wave functions. We'll just ask what's the simplest possible terms you could write down to characterize the system. And Chern-Simons term is the first term you can write down. We'll see all of this reproduced.
And not to anticipate, I should wait, but I mean, in the end, that's got to be the reason it works, right? Because as we've emphasized, the Loftian wave function is not exact. You could write another wave function, and so on and so forth. But they're all basically describing Chern-Simons.
We're going to see a loop of ideas. So we'll do Chern-Simons and show how it captures the same physics. And then we'll put Chern-Simons on a boundary, and on the edge there's a conformal field theory. And we'll see how the conformal field theory also captures the right physics. And the remarkable thing is, which I don't understand, that computing correlation functions in the conformal field theory will actually reproduce the law. So that's going to be the punchline for lectures, because that's the bit I really like. So we'll do this big circle. Okay, any other questions about this? So, I want to talk about other filling fractions. And when I first described the phenomenology, so that there were various filling fractions that emerged, various plateaus, and they kind of emerge in a particular order. And so what we want to do here is just explain the ideas behind that. There's going to be two separate ideas that we can discuss. As far as I can tell, they're really logically distinct. Both are going to give the same, more or less, the same emergence of fractions coming up. But the connection between them isn't quite obvious to me. So the first one is called the hierarchy. And the second one, the first one is due to Halperin and Haldane. The second one is called the composite fermion approach, and is due to Jacobs. So I'll just try and explain both of this. And I should say that it's going to be a little bit hand-wavy, but I'll try and tell you the bits that you can make precise and the bits that I think are still there. Alright, so firstly the hierarchy. Okay, so here's the basic idea. Is that we have a Loftin state. And the excitations in the Loftin states are quasi-holes or quasi-particles. Suppose that you're in a state where there's lots of quasi-holes floating around, and these are really dynamic objects. Then these quasi-holes are going to have their own dynamics. And there's going to be Coulomb repulsion between them, they go to fields, have background magnetic field. And so the basic idea is that those quasi-holes will themselves form quantum Hall fluid. So you have a background quantum Hall fluid, you have excitations of particles with fractional charge, but they form a new quantum Hall fluid on top of the original. That new quantum Hall fluid is going to have quasi-holes, which could form a third quantum Hall fluid. So you get this, what's called the hierarchy. It's kind of quantum Hall fluid on quantum Hall fluid on quantum Hall fluid. That's the basic idea. So the quasi-holes show particles. And I need a shorter word, so I'm going to call them quasis. I need either holes or particles. Form their own quantum Hall fluid. Alright, so what we're going to do is just think a little bit about what that means and come up with a prediction for the fractions.
So now, the problem you have to solve is to find wave functions that obey anionic statistics for the holes.
Yeah, roughly speaking, although as we'll see, from this approach I don't think it's possible to write down wave functions for the whole thing. From the composite fermion approach, you will write down wave functions. Rishi, I should tell you, we're just going to explain where the other fractions come from in the... We've done Loftin fractions now 1 over m, but we're going to understand where the other fractions come from. And this is the basic idea that the quasi-holes themselves, you'll have lots of them, and they'll form a quantum Hall fluid of the original. You'll have two quantum Hall fluids, one electrical and one small.
It is not like you are making a new theory for every new phenomena that you see.
You know, that's it, roughly. At the moment, it's going to. I think this lecture is going to be more intuitive than most. It's going to be less rigorous. But that's the. And it sounds reasonable. You know, these quasi-holes are particles with electric charge moving around in some background electric field. Water particles with electric charge in the magnetic field. It sounds plausible. All right. So let's just remember. So the Loftin state. Is there a question?
Yeah. So in a ground state there are absolutely no quasi-holes, right?
That's right. So actually, what you should think of is the following. Tune the magnetic field so you're in the Loftin state. Okay. Now move the magnetic field away from that of the Loftin state. What's going to happen? Well, one way to accommodate that is to put lots and lots of holes in, because you want to sort of lower the... So that's roughly the way to think about it.
So the extra assumption there that when you move away from that particular magnetic field, the change that happens is extra cool.
Alright, so the Loftin state, of course, is the product I of S and J, Zi minus Zj. So the M where M is odd for fermions and even for bosons. All of these quantum Hall wave functions have this exponential factor, e to the minus 1z squared, and it's just annoying writing it, so I'm going to not write it from now on, and I'm going to call this psi tilde instead of psi. So psi is just psi tilde multiplied by e to the minus 1z. Perfect time. Almost perfect time. We're going to talk about where the other fractions come from in the quantum process.
I'll understand each word.
So we did Laughlin last week, and now we're doing. Okay, and this is just for anti-symmetry purposes. So suppose we want a wave function for the quasi-Halls. So suppose we have anyons, and we write down a wave function for anyons. So we have two anyons with positions eta1 and eta2, and these are now going to be dynamical degrees of freedom. And we know that if they're anyons, if you exchange eta1 and eta2, you pick up a phase, which is not 1 or minus 1. And we know that from calculations last week, that this phase is 1 over m for quasi-Halls and quasi-particles, where the sign depends on whether it's a particle or a Hall. So it's plus for particles, so it's plus for Hall, and it's minus for particles. And there's implicit within that is the whether you're doing a clockwise or anti-clockwise rotation, and I can't remember. It's consistent choice of sign.
So exchange is like a pi rotation.
Exactly, exchanges of pi rotation.
So 2 pi rotation picks up 2.
Exactly. The calculation we did last week was a 2 pi rotation to get to 2, and then.
And what about when the hole goes around the particle?
Yeah, there is a mutual statistics there, I think. A hole you can think of as m minus 1 particles, because the rest is screening particles. So from that you can look, there is some mutual statistics. Okay, so this means that if you want a wave function, again, this is all going to be a little bit interesting, a wave function for many Halls.
So even if you get a rule that the wave function is not single.
That's right, and that's what I want to for many Halls, then the wave function should be I minus to j to 2p plus alpha, where p is something. Okay, why is that? I'll move one Hall around another. This being an even integer doesn't contribute to the phase, and the alpha as eta j moves around eta I is going to give me precise ones. So it's a non-single valued wave that we're working with if we.
So is this a genuine wave function? Does it?
Do you know what? I think the answer is no. So the bit you missed is we're going to do two approaches to understanding these other filling fractions. We're going to start with what's called the hierarchy, and the idea is that the quasi-Halls and quasi-particles themselves form a quantum Hall fluid in the background of all of this. And the other approach is going to be the composite fluid. The problem with doing this approach, what do you have? You have a bunch of electrons, and you don't really have, it's the Z's, the positions of electrons that you want to write down a wave. And in the composite fermion approach, we'll do that. Here, I don't know how to start from something like this, which is a little bit heuristic, and end up writing down a wave function for the Z's, which is what we want. So I think at the moment you should take this as
unphysical object. Some
hand-waving way to understand what's going on. But I think not very.
Can you remind me, why is the usual rule in quantum mechanics that a wave function has to be single?
Yeah, that's what I was going to say. I don't see why it should be. Suppose I just took a particle in a circle and I put a flux through it so that the angular, it's no longer quantized in integer units. Wouldn't the wave function not be?
We had this discussion where you could either
gauge issue.
You could either insist that it's single valued, or you could work with some boundary conditions and ask this. So it's not so much the non-single valueness of the wave function. It's the fact that etas aren't the dynamical degrees of freedom.
They're not the z's, but
No, they're not the z's. So the etas are related in some very complicated way to the z's. And at the end, you want to write down the wave functions for the z's.
but the rule for the z's will be single valued wave function.
Has to.
Yeah.
Why has to be?
Why?
Why has to be? I don't see it. It's
Let me
just
just say,
a,
it
it's
will
a
be.
bundle, right?
By the end of this lecture, I will write down
When
single
I write
valued wave
Schrödinger's
functions.
equation down,
Yeah.
Physical interpretation doesn't require
no, but the Schrödinger equation is not written in terms of mod size, but
Yes.
it's set derivatives.
Yes.
So what you do at the non-stable value is at the front, it adds up.
With the delta function, whatever the non-single valueness will give you. That's got to solve the wave function.
Contribute to some unit energy, no?
Does it have to?
I mean, one derivative already is a delta function, no? From the branch, right? And you could take two derivatives and stick it into a Schrödinger.
What if it's e to the I m
No,
theta
so
for
gauge is
integer?
gauge is a different thing.
No, but everything is.
So, for example, the point that the superfluid wave function is single value comes from the fact that you could cause infinite energy not to be, and that's why flux is quantized. That's why the flux quantum that gets trapped in a ring is a multiple of the elementary flux quantum, so that when you go around, it is in pi.
I don't know. There are many things. If you have particles of integer charge, then the flux you got to get through non-trivial volumes have to be 2.
No, so I'm just saying the one place I know where you can actually ask this question experimentally, right, is the many-body wave function of a superconductor on a ring. And then you pull it down in the presence of a field. As you pull it down, some flux gets trapped. It's always an integer multiple of the flux quantum, h over h, because the phase that the wave function picks up must be 2 pi 9.
I think there's just different ways to approach the same problem. Well, one very obvious thing is if you have a Dirac model, and you ask for a wave function for a particle moving in. You can either work with Dirac strings, so things become singular, or you're obliged to work with multi-valued wave functions and just patch them
Then
together.
patch them, right?
In some way.
Yeah.
But as long as you're careful, both will give the
So,
same.
but that's a gauge transformation,
It's always a gauge transformation.
right? But
It's a phase.
But the question of whether you pick up a non-pi phase,
If you're careful, you'll get the same answer in both approaches. None of this is going to be important. But we'll use this as
if
some
what you're saying is
heuristic
really true, then why should a superconductor always trap integer multiples of flux? A ring.
This is the calculation we did a few lectures ago, right?
Yeah.
We put the flux through a ring and asked when does it see it? And as Shiraz pointed out, there's two different ways to do the calculation. Either you insist on single-valued wave functions and you see the energy shift, or you allow non-single-valued wave function, you're just careful about the boundary condition, you get exactly the same.
But when you say careful about the boundary condition,
I think you're not saying when you fill out the ring.
exactly.
There, it's just physical results.
So, I mean, we're not saying it always has to be multi-valued. I mean, we're just saying sometimes it can be.
No, but then you're actually not talking of the same ring, you're talking of a twisted ring. You're allowing yourself the freedom to twist the boundary condition. Right?
This is just going to be a big inverted commas.
Let's go on.
We'll do it properly, sure. Okay, actually, properly is too strong. We'll do it with non-single value. Okay, so what's the? We're just going to count the filling fraction, okay? And it's the same calculation we did before, except we're going to just have to be a little bit careful. Yes,
Sorry, I have a question about that wave function.
No.
Not linear single valued.
Go on.
Yeah, so not linear single valued. I'm not worried about that. I would interpret this by there's a wave function for just n holes sitting around, right?
Yeah.
Zi minus theta, Zi minus theta. Blah, blah. So suppose you just multiply this to that guy.
What's that like?
The wave functions which is Zi minus theta 1, Zi minus theta 2.
No, it doesn't. I don't think it makes sense because you've got to decide what your dynamical degrees of freedom. Z's are the dynamical.
Exactly. So I have
not. Each are always parameters of those.
I'm trying to give a prescription for writing that as a wave function for this and asking what's wrong with that. So
we're going to do wave functions later in the lecture.
I think it's kind of like changing ensemble, because this has a fixed number of polygons, and you're kind of talking about different states of the fixed number of polygons. It feels like you've moved from a...
So, it's a question of whether objects are parameters or dynamical. I don't want to. I want to do one thing with this wave function now, which is count the number of quasi-holes and how high is it, and then we'll do wave function. So it's the same kind of calculation that we did. Before. You just sort of read off from this, what the highest angular momentum of the quasi-hole is, eta to 1. And it's given by this, where n is the number of quasi-holes. But this is the
is it that in quantum mechanics, physical observables have to be single value?
That's not good there. That will take us the other way. The answer to that, I think everyone will agree is yes.
Okay. So the area of the droplet, if you remember that, this angular momentum that describes a particle on a ring of some radius. Okay? So if you remember what that is, 2 plus or minus 1 over m. And then there's a curious factor here. So the radius of the angular momentum, if I take the lowest Landau level wave function with particular angular momentum, it has a radius that's proportional to the square root of the angular momentum times the magnetic length. Okay? This is the area, so it's the angular momentum itself times the magnetic length squared. And there's a factor of m here, which is because the effective magnetic length is h bar. The magnetic length has the charge of the object in, which is 1 over m. So that's where that factor of m is. So the number of electron states. So I have some area of a droplet with a magnetic field. The number of electron states is just the number of states in a Landau level. So that's the number of electron states that can fit into that area. The number of quasi-hole states that can fit into that area is m times this, because each electron will be m quasi-holes. Which means that the number of quasi-hole states, not the number of quasi-hole, the number of potential quasi-hole states in this droplet, number of quasi-states is MAB by 0, which is 2p plus or minus 1 over m squared n. Right, so this is the number of possible states in an area of that size, but the number of actual state particles is just n. So this means that the fraction of quasi-particles is minus plus 1 over 2mp m squared plus or minus n. Which means that the filling fraction itself is the original 1 over m from the first quantum Hall fluid plus the quantum Hall fluid of the quantum. Alright, so that's the formula that I wanted. That's all I wanted to derive from this idea. The Lofgren state, the quasi-holes above it form their own quantum Hall state indexed by p, and this is the resulting filling fraction. Are there any questions about that? I went through this very fast.
Just sorry, but just having a little trouble. The area is what I should be putting in here, right? Am I missing something?
The area should be in this. So this is the area.
Correct.
The quasi-holes are making, and you can plug it in.
You can plug it in here, and what was the n? I'm sorry. N is the total.
N is the number of quasi-holes.
The number of quasi-holes. I see.
Maybe I'm missing the background, but I didn't understand this last addition. Sorry, that was filling fraction of quasi-holes and then we added what?
So this was the filling fraction of the Lofgrens.
And that is of electrons in the electrons. Why are you adding filling fractions of electrons and quasicons. These are not different topics.
What do you want to know at the end of the day?
Where electrons are, right? We can't remember actual electrons, and quasiballs and absence of electrons. So there's a background number of electrons through one length, and then some absence.
So in a Lofton state, there's a significant fraction of quasiballs, density of quasiballs throughout that. Quasiballs lowers the overall density of charged particles.
Right. And this filling fraction, that it's counted with a minus sign. That plus is because you're counting quasiball occultation.
One is for holes and one is for particles. So a quasiball is a deficit of electron charge because you can't.
So the minus is for the particles.
Yeah, the way it's going to work, let me just draw a little diagram. So this is our usual rho xy versus b, and let's keep the classical result somewhere. Let's take the third, to be specific. And what we're arguing is that there should be other fractions. You'll see there's a bunch, higher b and lower b, which is smaller filling fraction and higher filling fraction. These are going to be the holes, and these are going to be the particles. So that's the way the sign should be.
Should it be nu quasi by m in the last equation?
Nu quasi by m divided by m.
Yes.
This is the right answer. So if the algebra works out, I don't think so. I think it's this.
Like m quasi particles form one by one m.
I think this is the right answer. We'll rederive this in another way. So let's just do an example. We'll take u equals a third.
Maybe the m cancels because the density of the fully filled quasi-particle band has m times as many quasi-particles. This is a fraction, right? So what you want to do is count the actual charge. So it's fraction times charge of a fully filled band. So does a fully filled quasi-particle have m times as many quasi-particles?
Yeah, we can put that there. Okay, so let's look. Suppose that the quasi-particles. So we'll start with the nu equals third state. Suppose the quasi-particles themselves form a Lofton state with p equals 1. Then what do you get? You get u equals 2 grams. But that's the most prominent, second most prominent pattern. That's the sign. So it gives the right. It's being experimentally observed. Suppose the quasi-holes equals 1. Then you get nu equals 2 sevenths, and I don't know if that's been observed, to be honest. Certainly in all the famous plots it hasn't, but the hole is this way, and 2 sevenths is quite a long way this way, and it's very high magnetic fields, which I think are not really accessible. So I'm not sure. By the way, I should say this approach sort of works for some things and not for others. The other approaches.
Sorry, just to understand. So we get nu equals 2/5.
Yeah.
And then the physical picture again is that we have the nu equals 1/3 state, and then we have quasi holes in that, and then there's a fractional Hall state of the quasi holes.
Yes.
And then, I mean, why is that the ground state? Nobody knows.
They're nowhere near the level. When we do the composite fermions, which we'll do in about 3 minutes, I'll tell you where things look a bit more interesting.
Oh, you mean you never see nu equals third? You only see nu equals 2/3?
No. So as you vary the magnetic field, you saw lots of fractions. But the idea is that as you vary the magnetic field here, the 2/5 state should be thought of as the third state with the quasi-particles themselves forming a new quantifiable fluid.
Are people sort of certain that these are ground states rather than could there
We'll
be
talk about states shortly.
all I mean is could there be some like hysteresis? Could it be that the reason that
We'll talk about states shortly. So if you look, so now the new quasi objects can form their own quantum functions. And you can redo the calculation. But the calculation is actually easiest done in the Chern-Simons theory. So I'll write down Chern-Simons theories for all of these states, and there it's much more easier just to write down to compute the filling fraction. But what it turns out is you get these nice partial fractions. Sorry, not partial fractions, they're continuous fractions. So these are the sort of filling fractions that are.
These are the quasi-holes of the quasi-holes.
These are, yeah, quasi-holes of the quasi-holes.
Turtles all the way.
Okay, it's fine. Let's look at quasi-particles. So we'll start with the third state. And then for each one we'll put p equals 1, which is like the first quantum Hall state that they make. So these fractions are a third to 2/5, to 3/7, to 4/9, 5/11, to 6/30. This whole sequence is seen very, very clearly in experiments. So it's sort of quite compelling to get the right answer. Well, the answer that matches experiments.
And each time you fill out just the lowest lambda level of that.
Yeah, so now you can start asking, what happens if you put p equals 2, or what happens if, you do a particle and a particle and a particle, and then why not a quasi-hole? None of that works. So it sort of works on this very crude level. I'll just pass this around actually. Look to the left of a half. To the left of a half, to the right of a half. Sorry, to the right of a half. And you can really just see very clearly these fractions being seen in this graph. It's quite.
This is the chain sequence?
The chain sequence is the same, but comes from different physics. This is not obvious to me as the same physics. So, it works. It seems to work impressively, but maybe only if you squint and don't try to put too much faith in it. Okay, any questions? Yeah, please.
So this whole approach seems to be some sort of perturbation theory, right? That the effect of extramagnetic field is exactly the effect on the ground state of radiation magnetic field. So in particular,
Perturbation theory makes it sound like we've done something trustworthy.
Yeah, sorry, I'm being point is that there will be competing things on the other side, right? What happens is you also get a state from adding quasi-holes and adding extra magnetic field with a nu equals 1 after 1/3, right? It's like at some point this should break down and you should.
You've got lots of integers here that you can play with, and lots of sequences of fractions that you can get. Most of those are just instant. But if you look at very specific ones, then
there should be a cutoff above, after which only m equals 1 such a space term. The states you get from m equals 3 and add other integers. And the states you can start with m equals 1 and add other p1s, please. Right? So is there a cutoff of filling fraction, above which you only get states that you get from starting with n equals 1?
you should play it out. Okay, so this is sort of the basic idea of the hierarchy. And it's quite nice and physical, this idea that these quasi-holes form, quasi-particles form Hall states. I don't know what other evidence there is for this.
So just from this argument, nothing prevents you from becoming irrational. Like irrational numbers can have partial fractions which are
Irrational.
repeat. Yeah.
After
It's never
It repeats.
but these are becoming more and more delicate as you go along. They're becoming smaller and smaller.
I think taking this to infinity is taking the argument too seriously.
Actually, it works. If you take this to infinity, I think you get a half.
Yeah.
And a half is exactly where we're going in this section. The half is the most interesting part of this whole right. So as people have been saying, it's clearly not rigorous, and I'm not sure if there is evidence that this is right. I don't know what the evidence would be that it's the quasi-holes that. It sounds compelling, but I don't know if there's any other evidence. So there's another approach to this, which is due to J, and it's called the composite flow. And we're going to see these same fractions emerging, but the other fractions that are sort of somehow less compelling don't emerge, so it looks better. I'll tell you the basic idea as I understand it. The basic idea is we have some strongly interacting system, and it's often the case in a strongly interacting system that the degrees of freedom that you care about are some emergent degrees of freedom. And in fact, we've already seen that here. The degrees of freedom you care about are these adions, these So James' approach, and I think it was fairly controversial when it was first postulated, is to say that to give a suggestion for what the relevant degrees of freedom are. The slightly odd thing, from my perspective, is that these relevant degrees of freedom play a role in the intermediate part of the calculation, rather than the things that you actually get to see and play with at the end. Which puts it on, I think, a slightly dodgy footing. There's one exception to that, which is kind of the highlight of this whole story, a quite astonishing highlight, which is what happens at nu equals a half, where these composite fermions really aren't the things that you see in experiments that are moving around. So that's sort of where I want to get to at the end of this lecture, is to tell you about why nu equals a half is special. So let me tell you what the Jane story is. A lot of it is not stuff that's that familiar to me as a field theorist. And you sort of hear, I heard him give a very nice talk on this actually back in January. First time I'd really heard of this. You think maybe not, how can you tell? But I'll tell you what the successes are. There are genuine quantitative successes.
So one you say that's more dodgy than this or not?
No, I don't think it's any more dodgy. I think it's better than this. Because we'll be able to test it in certain ways. So if it passes tests in a way that it passes tests, as far as I can tell, much better than you should have anyway. So I think it's better than this.
So just a basic question about this, just showed my ignorance. About any one of these states, let's say you've got the one-third state, you're saying these quasi-holes are effective low-energy massless excitations. So this is not a gap state.
No big gap.
Yeah. And what are these quasi-holes?
They're big excitations about the gap.
They're massive excitations. I see. And their mass, the mass is like the first Landau level of the quasi-holes. It gives the gap. The first. So the quasi-holes have some spectrum. What is that spectrum?
I think that's complicated. It's something you can easily get from
I shouldn't think of them as effect almost like free particles moving in a magnetic field.
When you vary the magnetic field away from, sorry, I had this picture here. You have magnetic field at the nu equals third. When you vary the magnetic field away, it populates these quasi-holes.
Yeah. Wait, then probably I didn't understand this 2/5. I thought the idea was that this 2/5 is like quasi-holes filling out their own Landau level.
That's right.
So it's not like at any other fraction you have quasi-holes that are not enough to fill out their own Landau level.
They're not filling out, of course. They're in their own Lovelock state. So they're in a very particular fraction.
Right. So suppose I'm sorry, but I have this one-third state, and I move my magnetic field. I've got these bunches of quasi-holes, and it's not correct to think of them as effectively free moving in a magnetic field, because the 2/5 you're telling me it is
free is
almost free.
Their Coulomb interactions are important because they want to drive you to.
Okay, maybe almost Laughlin. Okay.
Yeah. So wherever at some particular magnetic field, there'll be at the filling fraction that allows them to form that Laughlin state.
Right.
And that's kind of where they lock in. They then form the gap phase above that. They have their own little plateau. And that's where the
So you're saying before that they're not free, but they're behaving like free electrons, but not free. There's interacting electrons in a magnetic field.
Yes.
I see. But these interacting electrons, had I taken away the interactions, would still have been gapped. And the gap would have been given by the first set, the energy of the first Landau level?
No, I don't think that large. I think the gap is just a complicated thing that we don't have access to.
Right. Thank you.
All right, let me tell you.
Do we know anything with one quasi-hole? One quasi-hole. So the interactions are between two quasi-holes.
Mm-hmm.
So whether I just take the state and add one quasi-hole, then do I understand that state?
I've not written down any state. The only time I wrote down a state was in the last lecture, which was one quasi or many quasi-holes above the loft level.
Yes.
But those were parameters. Those etas weren't things that could move around. So I've never written down wave functions here. I'm going to write down wave functions.
I'm sorry,
because I don't really understand.
And what was the argument that there exist these quasi-holes and quasi-particles?
Oh yes, so we pulled the wave function out of thin air and then described its properties as fractional charge and fractional statistics. The best way to think about it is you take the Loftin wave function, you write down a local Hamiltonian which has that Loftin wave function as its exact ground state. You then look at the excited states in that local Hamiltonian, but they're equal to these.
There you see.
These quasi-hole states. And then you argue that if you deform the Hamiltonian, the Loftin state changes, but its universality property. Universality includes statistics for these objects. All right. Let me give some definitions. So it makes it look as if I'm going to say something precise. And then I'll try and give you some physics. So a vortex. And I have to say, when I first came across this, I was a bit nervous because it's not what we usually mean by a vortex. A vortex is a place, so it's a place in space on the plane, where the phase of the wave function winds by 2. Okay, and I'll give you examples. Let me just stress, usually by a vortex we mean order parameter has a phase that winds by 2. Okay? This is not that. The wave function is not to be confused with that. So it's really something different. I'm not sure how different name. It's always called a vortex.
There's a wave function for z's.
Wave function z's, as a function of z's. So let me give you an example. When we looked at the quasi-hole wave functions, we saw that you take the Loftin wave function and you just multiply it by this pattern. Which means that as you move any of the z's around the point eta, which was just that chosen parameter where the quasi-hole sits, the wave function winds by 2. This is an example of it. In this language.
Precisely means if you fix all of the z's to be, if you take all of it to be anything arbitrary, but then move one of the z's around that point, then you get a 2. Is that right?
Yes. Yeah. This fact that there's a 2-pi winding around this, if you go, you look pained. Is it okay? Yeah. Okay. This is actually what was responsible for those Berry phase calculations we did in the last lecture. So it's actually this winding of the phase of the wave function, which was responsible for the fractional statistics that was causing the wave. So it wasn't something we stressed in the last lecture. Ultimately, that's what's responsible. Okay. Now look at the Loftin state. So the Loftin state at level n. Again, psi tilde means I'll drop all those exponential factors. Is of course this. And I'm going to take m to be odd. So I'm really going to think about electrons which are fermions rather than. Alright, so it's very striking that this has m zeros all of the same place. One of these had to be there by Pauli exclusion. When two z's come together. Basically, Pauli exclusion principle and the statement that in the lowest Landau level, things are followable. So 1 0 for one winding is required by Pauli. But sort of the defining feature of the Loftin wave function is that the other m-1 zeros sit at the same place as the one here. and 0 to the things we call vortices, is sickness.
So if we think about what's special about the Lofgren state in universality, is it precisely the one where the forces are bound?
That's exactly right.
Precisely
Yeah.
So that's what's kind of not generic about it.
That's what's special. So the definition of a composite fermion is to think about these vortices as somehow acquiring a life of their own. I'm not quite exactly sure what that means. But the idea is that the composite fermion is the original electron bound to n-1 extra vortices, which is motivated by the formula. So we're going to sort of take this idea and run with it and see where we can get. So there's an electron attached to n-1 vortices. Okay, so this is the definition of composite. It's not obvious it's going to be useful, but as we'll see, it turns out you can do things. Alright, so the next thing we're going to do is the kind of experiment we did before. We're going to take this composite fermion and we're just going to move it in a big circle inside the Lofgren graph. So move composite fermion CF in a circle. That's the whole droplet. We'll take composite fermion. Last time, of course, we took a hole. Now we're taking a composite fermion and we'll just move it in a circle. And we'll think about the Berry phase of the composite fermions. So the Berry phase is there's the Aronoff-Bode phase and an electron as it moves in its background. So that's just A is the area inside B. B is the background magnetic field that it sits in. Atom, B obviously stands out. So this is the Aronoff-Bode phase. But because this winds m times rather than just once, there's an extra contribution to the Berry phase. Which is due to these vortices, and A is the density of electrons. So it's the same kind of calculation we did for a quasi-hole. For a quasi-hole, we computed the Aronoff-Bode phase. It was less than that for the electron, but we interpreted this as a smaller charge for the quasi-hole. Okay. Here we compute the Aronoff-Bode phase, and it's more than that.
Just to understand, so you compute the Berry phase by changing some parameter.
There's no parameter there.
Yeah. So just
yeah. So somehow. Yeah. So the best thing we'll be able to do would be to fix Z, and then just move this around.
fix all the other Z's maybe, and then you move.
No. Let the other Z be the dynamical degrees of freedom. Fix one Z.
Yeah.
Then can
You are moving the full thing around, right?
Which whole thing?
The full wave function is moving around.
No, just one composite fermion from within
The
all.
whole thing is one composite fermion.
No.
This is a very
There's one composite fermion for a given electron, so they're in one-to-one correspondence. But it's the electron plus the addition of these windings of the wave functions. That's the composite.
Isn't it just that you move one of the CJs around,
Yeah.
but make sure that all the other ZIs still have a threefold zero at the place? ZI only moving one.
So if I take the Lofgren wave function and I just make one of these a parameter, then I literally compute the Berry phase.
Yeah.
So I move that around.
Right.
I think this is this should be what I get.
Yeah. I see. So that's what it is.
So you're just interpreting that as the statement that I've taken one electron and two vortices bound to that electron and moved the whole thing.
working with n equals 3.
Yeah. I think that's the one that makes sense.
So the claim is that for the quasi-home we thought about this as having a different effective charge, but really what you see in these calculations is charge times magnetic field. So we're going to have a slightly different interpretation here, where we're going to think about this composite fermion as still carrying the charge of an electron, but experiencing a lower magnetic field due to this very effect. So the idea is to interpret this as moving in a lower magnetic field. That I'll call B star.
Interpret what is moving to the lower magnetic?
The composite fermion. So the electron moves in a magnetic field B. The composite fermion is the electron bound to these vortices. This is going to be a new object that's going to move in.
And then plus sign, why is it the lower magnetic?
We'll see. So gamma is 2 pi A B star goes by 0. And maybe it's a good base. Which means that B star is B minus n minus 1 times.
And the minus sign is because an electron picks up a phase, one phase, if you take a vortex around it, picks up the minus phase.
Must be, I wasn't there.
Because one is the 2 pi rotation, the other is minus 2 pi rotation.
But I mean, this is that could be an interpretation, but the calculation is the calculation. Right? You write the wave function down.
That's right. So there's an interpretation of this stage, and at the end of this lecture, I'll give some very compelling evidence.
So when we did the first calculation of charge, again, since we were talking about Aharonov-Bohm phases, it's only EV that matters.
Exactly, yeah. So
we could have even interpreted that as carrying E and working in a field to be choose left.
That's right. And maybe it would have been slightly off there because you knew the electrons were in field B, so why would the other object be in a lower field? So maybe it was more natural there to interpret this. Let's change each charge. But yeah, and all of this is kind of hand-wavy, intuitive part that I don't think you can rigorously derive. It's just the.
So here the motivation for thinking in terms of effective field is what happens when you move the farm. Right?
No. That's going to be the consequence. That's going to be a very striking consequence.
No, but I'm saying, as you said, you could think of this either as some E star times V or E times V star.
There'll be lots of motivations for thinking of this, but that's the most striking but only consequence. Okay, so what does it mean? It means that if composite fermions experience B star less than B, then there are fewer states in their lambda levels.
So maybe this was said that instant. So what is the interpretation then that the lessening? Did you give that or
the interpretation of
why it's becoming less? There is
as opposed to more.
No, something gets attached. Did you say that?
So there are electrons, but the electrons now have these vortices attached to the vortex. And the vortices give an extra contribution to the berry phase because their phase is.
So I would say that the vortex is a zero in the density of electrons. So moving the vortex around is kind of like pushing the electrons the opposite direction. So it's like an absence. It's a rough way of thinking about why it's to the minus side.
No, but I mean, I think the minus sign is clear from what you said.
Yeah.
You said that an electron going around a vortex picks up 2m pi. Therefore, a vortex going around an electron picks up minus 2m pi. Because these are constants. And now you're taking the vortex on.
Alright, so the density of electrons
2 pi
is UV over pi 0. This is the Filling fraction. But there's one composite fermion for every electron. So the density of electrons is the same as the density of composite fermions. Which means the filling fraction of composite fermions has to be different. So the filling fraction of composite fermions is U star. I'll use this formula here. So it tells me that the filling fraction of electrons is related to the filling fraction of composite fermions by the following. particular, if I take mu star equals 1, which is just a fully filled Landau level for the composite fermions, so it's the integer quantum Hall effect for composite fermions. This gives mu equals 1 over m, which is the Lofgren state for electrons. So the first idea is that this is a unification of the integer quantum Hall effect of the fraction. The new objects are the composite fermions. If you fill them up to an integer quantum Hall state, the electrons will experience fraction.
So actually one thing I'm not understanding is that both the electrons bind these m vortices, then the phase won't be the right one.
Both the electrons.
Meaning you've got Zi minus Zj. So it sounded like you were thinking of one of them as just an electron and the other one as a composite fermion in order to get the right phase.
Otherwise I have an S.
Yeah. I mean, his motivation was that you take Zi minus Zj, the whole thing to the power n. You want to understand why when you wind around, you get m. So if you think of one of them as an electron, the other is a composite fermion, you print it up to get m.
Yeah.
But why is that one special? Presumably they're all composite
If
fermions.
it's m minus 1,
M minus 1.
it's m minus 1 squared, which is the way the statistics goes.
Maybe it's not m minus 1 because around vortices you've not told that's what the rule is. It's electrons with vortices and vortices with electrons, but you get some factor of 2.
I don't know.
That was just the wave function of electrons, right? It's not the wave function of composite.
We'll see wave function shortly. We're not doing wave function.
No, I'm saying just at the basic level of an interpretation, how should I think of each of these? If I think of each of the Zs as a position.
So ultimately we're going to think about sort of non-interacting composite fermions.
And those non-interacting composite fermions sit at the Zs.
Yes.
Yes. But then I don't understand this basic.
So we haven't exchanged composite fermions around each other. Right? We've only moved.
Taking one composite fermion
and
and moved
space.
it in empty space, yeah.
But I thought the
Using
basic
the very
idea was that.
phase that arose from that. So is
No, but I thought the initial motivation was that you wanted to get this factor of m. So you took Z1, Z2, you moved Z2 around Z1.
sorry, we didn't. That was against a factor of m in what? In the wave function.
No, that when Z2 moves around Z1, you get 2 pi.
You get extra m minus 1. That's the
Yeah.
But what you really do is you move Z1. You don't move Z1 around Z2. You move Z1 around everything else. All the others are dynamical degrees of freedom. They're not anywhere in particular. But they're the things you integrate over when you compute the variables.
No, but you started the whole thing saying, look, we know we have to get, one interchange, one factor of Z1 minus Z2, but actually we've got Z1 minus Z2 to the power n, which suggests that you've got m minus 1 additional things binding to Z2. But that doesn't work if you've also got a binding to Z1. Or maybe
But Z1's, only one of them is in the game. Everything else is just integrated. Right? The very phase calculation is the overlap of those two
Wait,
states.
am I not supposed to think of the composite fermions all sitting at the Zs of your Lofgren wave?
Yes.
Then if so, why do I get Z1 minus Z2 to the power m, given your composite fermions?
So it's a question of a calculation at this stage. You do the very phase calculation.
Of just Z2 going around.
No. Everything else is not at some position. Everything else can be anywhere, right?
No,
So
I just want to understand why I get Z1 minus Z2 to the power m. I'm uninterested in everything else. Okay, so I want to understand why if I get Z2 around Z1.
Sorry. The starting point is the wave function has Z1 minus Z2 to the power n.
Okay, but I want to understand why this is true now, given that you've given me a new interpretation of this wave function. Hasn't it?
But this we're getting to.
Okay.
So the only thing so far is that's the starting point.
Okay.
Now, you compute the very phase and you get the extra contribution.
Sorry.
And now we're going to think about these individual.
Sorry.
Is that okay? So let's see. I think.
No, I guess the conclusion is the interpretation involves some words. Now, if I want to use those words and write that wave function,
Yes.
how does it go? That's what
So this is what we're doing next.
Okay.
Yeah. So let's write the wave function
For
just the Lofgren wave function. let me tell you where we're going. We're going to write down wave functions for all these hierarchy sets. Okay? We're not going to rigorously derive them. We're going to just, with a bit of intuition, think about what this means. So let me write them down, and then maybe we can argue about whether this intuition is correct.
You mean you're going to give up the rigor that you've had so far?
Exactly, yes. It's getting even worse. And the reason I'm doing this is because it works spectacularly well. I'd like to explain what the spectacular successes are. If this could be made more rigorous, this would be. I really think this would be important. Okay, so Zi minus Zj minus 1 minus L. Okay, so this is the way you write a wave function. It's a completely trivial. Completely trivial factorization. This, of course, is a fully filled Landau.
Yeah, last thing Zk minus Zl. Is the last thing Zk minus Zl?
Yeah. And this is going to, you're going to attach the words to this, that this factor attaches m minus 1 vortices to every element. Okay, so it's just some words.
I think it's these words that were confusing. I think the way to say it perhaps is that every electron sees every other electron as having a double vortex bound.
But you should think of this as a composite fermion going around.
I don't think so.
That will be visual statistics of composite fermions. That's not.
The statement is every electron sees a double vortex at the position of every other electron.
But the electron is an electron.
The electron is a. But the fact that it sees a double vortex at the position of every other thing, then you can write as a composite fermion. But that's not obvious from that.
No, but it's a very strange interpretation given that you're saying that it's, for a particular electron, everything else is a composite fermion, but the electron itself is an electron. It doesn't seem democratic.
But for the other electron, there's a double vortex at this position as well.
Okay, so but then what, suppose you wrote out a wave function for the whole thing.
So I'm going to write down a wave function for the whole thing. Let's write it down. No, obviously not. This is trivial. Let's get to something.
Okay.
There's a reason I'm doing this.
Okay.
There's some results. Okay, so let's look at something here.
The whole motivation for this is useless now.
Okay, so if you plug into this formula higher Landau levels, 1, 2, 3, 4, 5. So we take the composite fermions and we put them in an integer quantum Hall effect, but now with a fully filled mu star number of Landau levels. Then the news you get out are exactly these. Okay, so it's exactly the same hierarchical fractions what we saw. The ones that were very successful in reproducing the
I missed this. So what were you getting at? Doing to get these fractions again, please?
I've put the composite fermions in an integer quantum Hall effect or a used
with a different
integer numbers.
So that means you keep this factor of Zi minus Zj to the power m minus 1 fixed.
We'll see.
And changes the rest.
We'll see, yeah. Okay. So now, given this here, we're going to try and write down a wave function for these things. Okay? So in some sense you could think of all of this as words which has given us the courage to try and write down the wave function for these states based on this situation. Alright, that's the way to do it. So what is the wave function? There's some weird thing in front, which is horrible and I'll explain later. This is the wave function for mu star filled Landau. This is analogous to this. This was the wave function for a single filled Landau. You just replace it with the wave function for
mu star.
Mu star filled. So this is mu star filled Landau. These are three objects.
And what's the value of n? It's always 3 now, or?
In this case it was for 3. That's right. But in general, there's a set of mu's for every m. So this is the more general. When m is 3 is vacation. The problem is that it's only the lowest Landau level which is holomorphic. Okay? So the wave function for these, it's very easy to write down because they're just free fermions, and you know what all the wave functions are, so it's just a slated determinant. So you can write down this explicitly, but it's not horrible. But this obviously sits in the lowest lambda level, so this better be. So that's what this guy here is doing. This guy here is not uniquely defined, as far as I can tell, but there is a sort of standard standard definition that's given for this. So PLL is projection to the lowest lambda level. And the operational definition is the following. You move the Z bars to the left. So any Z bars that appear in here, you move to the left. And then you replace the bar I goes to 2 and B squared. It's a brutal operation. It's not something nice in a Hilbert space. It's not a unitary operator. It's something completely horrible that we're just doing to functions to massage the function into a formula.
That's this operation on the lowest lambda level that would give you the Z bar. Because the lowest lambda level has an
If you like, it removes that number of angular momentum. So it works on that quantum number level.
No, I'm saying just in terms of the wave function, there's the Gaussian part of the wave function.
You don't do it to the Gaussian part. You just do it to the part that's here.
Oh.
Yeah, that's it. There's an e to the minus here. This doesn't act on that.
Oh.
Just acts on this.
So maybe we get lost somewhere here. How do we get the Z bar
Because this is
what's a higher number?
Yeah, these are 2, 3, 4 field backgrounds. So this always comes with a Z bar.
What's the ordering prescription?
Sorry?
What's the ordering prescription?
The ordering is you move all the Z bars to the left. Of course, it's just a function here. But as soon as you replace Z bars with an operator, it doesn't matter. So you just
When you write a 2 by 2 Z, which order you keep it in matter. Right? You put 2 by 2 Z on the right here, you have function which is.
So it's acting on that.
So that's what he said. You go to the left and then make it.
Yeah.
Well, now there is a natural definition of projection, which is just thinking of these as states in a Hilbert
This
space.
doesn't work. Then it's 0. Because this is not a state at the lowest lambda level.
But that times the Zi minus Z shape has some projected part in the lowest.
There is some.
They're orthogonal. In a Hilbert space, so it's definitely not.
Oh.
Yeah. It's something really horrible.
There is no piece of it at all.
It's a full many-body state.
Yeah.
I mean, it might have some overlap, but you don't know how.
No, I think the overlap is 0.
U star equals 1.
Yeah.
And why is the overlap 0?
Because
Z
it
bars
has components in the higher lambda level.
Yeah, it has components in the higher lambda level, but if I throw those components out, nothing survives.
Basically, every single term has a part of it. If you write down this out, it's a polynomial, and every term in that polynomial has a Z bar. Every time.
Every time.
Yeah. Because every term has a Z bar in there, it has 0 overlap with. It's not a lowest lambda level.
Because every term has a Z bar, then whatever you write it out, it's expansion in second and third and fourth and fifth, but nothing in first. Yeah.
Okay. So
Okay.
This is not a projection in the usual sense. we
No.
understand a projection.
Yeah, sorry, this is a bad name actually. It's not a projection. It's a brutal operation. The remarkable thing is that these seem to agree very, very well.
Where did this rule come from? Z bar, this replacement rule?
No, it's just, I think at some level it was the one that was easy to implement. Because there's lots of things you could imagine.
There's only momentum.
Yeah, of course, that's good. But it's the one that works. So this,
But you say it does agree very well with numerics.
with numeric, up to the usual caveats of 2020. And if you go to Jane's talks, obviously Jane has been working on this for 25 years. This is the thing that Jane did, this is the thing that Jane pushes. He's not unbiased. I think he's honest.
Yeah, he's given several talks. The numerics seem to be good, but
Many excited states that you can start to write down here agree with those. So, it all sounds very fishy, but it's clear there's something in there. What's more, the big success is what comes next. Are there people waiting outside? Is there a lecture?
Sit down.
just stop again. No. It's something that's people are talking.
Can I go on for 5 minutes and tell you why this is really amazing?
They're just talking. They're not trying
No,
to.
there's no one waiting. Someone in the office.
So, you know, all your concerns.
Before we go on, just to understand, so, I mean, many questions, but the basic point is that you take two vortices, as you define them, attach them to every electron, then you look at the remaining magnetic flux that survives, which is lower, of course, and then you just think of this composite fermion moving in this reduced magnetic flux. And that's why it's integer quantum Hall flux.
Exactly. Well, I can also choose to put these at some fractional quantum.
Okay, you can.
And then I get some other fractions, and I think some of those agree with what's observed in the data. Everything that's observed in the data works very, very well with this procedure. The way the fractions are.
Yeah, and then just to ask you, I mean, you emphasize that for the integer quantum Hall effect, this order was all important, and so on. And then, of course, just in terms of the numerics, and then, of course, we did the fractional quantum Hall where we said, okay, we'll look into interactions between the electrons, but not think about disorder.
We needed it to really explain the plateaus in the same way. It's just.
Did we even? I mean, it wasn't clear to me. Was Laughlin suggesting a wave function that would be a good approximation even without disorder when he did it for the three-body system?
No, you need it for the same reason. You know, you have a gap in your density of states. That's what Laughlin wave function knowledge is. But the argument needs to come to water. That's not enough to get plateaus as you vary. You need localized states.
Yeah.
So disorder has to be in the background here to really.
And so when you say that, for example, this wave function agrees with the numerics, the numerics has disorder in it.
No. These are, the wave functions, the disorder is needed to get an observed plateau as you vary the magnetic field and all the rest of it. It's not needed to get ground state wave function to be enough wave function to be. It's a question about what happens when you move away from that very specific beat, how the system responds.
I mean, if disorder is important to explain the Plato, it should be important to understand the ground state also.
No, I think there are two hierarchy. There's a hierarchy of energy scales. So the ground state is dominated by the interaction, the scale of interactions, which will give you Laughlin wave function, which has a gap. Starting from that picture where you've got a ground state with a gap, it's the disorder that's necessary to kind of populate the gap with localized states. So that as you crank up the magnetic field, you can start to populate more states, but they don't contribute to it. If you go back to the integer quantum Hall state, the disorder wasn't necessary for us to write down we didn't write down the wave function. We could have done very easily to say one field that is the ground state. It doesn't change much under the disorder. It's the nature of the state within that.
Right. But it's the state, I mean, if you're not sitting at some very precise value of the magnetic field and you wanted to understand the nature of the ground state,
yes,
then you'll need to see all important, right?
Yeah. So we're kind of tuning the magnetic field to that. One third field.
And so when we say things agree with numerics without disorder,
I mean,
for
that
those.
was very true.
But if we went a little away, then you presumably not agree at all.
Yes. Well, if you went a little bit away, you have nothing special in the absence of disorder. It wouldn't be typically in this state.
I suppose I now understand what Kedar was saying, that basically you should just think of every Z as position of an electron that sees every other thing as a composite fermion. That seems to be what you implemented before your projection.
That's right.
But the projection I cannot understand at all. Where did that come from?
You get some intuition for how you attach fermions, and now you've got composite fermions. So how you attach vortices, you've got composite fermions at some field Van Del level. You attach those vortices by multiplying with that factor, and now you find you have a wave function that doesn't make any sense for it. So you've got to do something horrible to it. So what do you I don't think it's anything more than that.
Okay. But you said this is not neatly defined. So is there some other prescription people use? Maybe we'll understand.
Yeah, many, and it seems to be fairly robust. Exactly.
So what is one? What is it? There's many ways of taking this you're saying and getting a function in the world.
I asked Jane explicitly in the talk I saw him give in January, whether this was robust to different choices of projection. He says that it is.
Yeah, in the talk he gave, which we both heard, he said something like full projection or taking derivatives. So what?
Yeah, no, he says what he implements numerically is not quite this,
Yeah.
because something else is easier to do numerically. But then he played with
Okay,
it really
he did
nice.
that.
Okay, let me tell you what is the gem of this approach. The gem has nothing to do with quantum Hall. And it's totally astonishing. It's the half-field magnet. Okay, so by this I mean electrons are unique. It's worth pointing out there's a Loftin state at nu equals a half, which is when m is equal to 2. But this is a state for bosons. So that's not what I'm talking about. I'm talking about electrons, which are fermions, half-field. And if you look at the data, there's no hint whatsoever of a plateau at nu equals a half. In fact, there's a region around nu equals a half, which is the biggest region in the diagram where there's no plateau at all. And so it's really just a straight line from rho xy. Rho xx doesn't go to 0 at all. It's as far away from quantum Hall status as you have anywhere in the phase diagram. Okay, let's look at this from the composite fermi approach. So consider electrons attached to two vortices. At a density which is half-free, which is n is d over n and phi, where n is the density, so 2 phi. N is the density of electrons and 2 is the okay. So taking this formula that we had before, this was the formula for the reduced magnetic field, and this gives 0. So the claim, if you're going to buy this composite fermi approach, is that you take electrons and you put them in a magnetic field of something like 25 Tesla. It's just astonishingly strong magnetic field. And we all know that they should go in circles. But the claim is that they form new emergent degrees of freedom, which we can think of as composite fermions attached to two vortices. And these composite degrees of freedom have the same charge as an electron, but they move completely free. They don't experience the magnetic field. It's really striking. So, the claim is that electrons in a magnetic field of about 25 Tesla become composite fermions and experience no magnetic field. Just calculate anything you want and compare to experiment and everything. But there's
it's a U1 transfer.
But there's some very, very simple things you can check to see if this is right. Which, as Kedar suggests, is you move the magnetic field a little bit away from it. So you just explore in this region. So now what you expect to have is a we were talking about earlier, just a metal in a very, very small magnetic field. The magnetic field is just going to be the difference from this. So what would you expect to see? You would expect to see things like the Hauss-van Alphen oscillations in the susceptibility. Or even more clearly, you should expect to see that the electrons which move in cyclotron orbits. They now move in circles. But huge big circles because its size is fixed by this tiny, tiny magnetic field. So you can do experiments to measure the radius of the cyclotron orbits. You see that it's exactly what's predicted by this.
And if I remember my undergraduate or whatever, then the D Hauss-van Alphen whatever also tells you something about the size of the Fermi circle.
So you can measure that and you can measure the degrees. Yeah, so everything
that
agrees.
agrees with what you would expect for so many electrons.
I should say that the Helper and Lee-Reed theory is much more sophisticated than this. It's a field theory, it's Chern-Simons, it has other motivations.
Sorry, go on. to ask you something again.
Okay.
Sorry, but just at the level of the wave function then, is this the same thing as before?
So
You put Zi minus Zj?
What's the wave function? It's I'm not sure what tests there are on this wave function. It's horrible projection operator. It's flux attachment squared, and then it's the wave function for a Fermi surface. What's the wave function for a Fermi surface? It's a Slater determinant. So what have I got here? The J's are the RJ's are the positions of the J particles. And the Ki are the first n momentum states if you put the system in a box. And this is the determinant over the I and J's, which will give you the wave function for a Fermi surface. This, of course, is K Z bar plus K bar Z J. And so it depends on Z bar, so this means you have to sort of differentiate with respect to
And this Halperin-Whatever theory is just free electrons coupled to U1 Chern-Simons with the charge that will give you this the right phase. But that will give you from
the charge means the level of Chern-Simons?
Yes.
The charge is 1, the level is a half.
The level is a half. And that's, I can't do that in my head, but that is what will produce
That will give all the...
But that's a bit different from the composite fermion picture because here each guy will be trapped differently.
Yeah, that's the point. So that's
what I was going to say. From the Chern-Simons perspective, I think composite fermion picture is the flux attachment from this emergent Chern-Simons gauge.
So I've noticed this sort of way of thinking where somehow Halperin-Levy is this sophisticated theory and Jayan did something uncontrolled. I want to know what's so sophisticated about Halperin-Levy, because as I understand it, you do this singular gauge transformation and then you've got this, because you've done this singular gauge transformation, you've got this other field whose flux is actually tightly bound to the positions of your electrons. And then you do a mean field theory where you smear it out. And it's just a mean field theory, right? So why is mean field theory more sophisticated than writing down a wave function? At one level you're doing an uncontrolled mean field theory. At another level you're doing an uncontrolled projection. So why is one more sophisticated than the other? I've never understood.
The whole mean field theory approach to the Chern-Simons, I don't like.
Okay, good.
And I think there's a better way to do
Alright,
things.
good. So you
And the better way to do things is to, there's a dual Chern-Simons theory, which has the advantage that its level is quantized. It's the approach that Wen and Bloch and Z.
But that's not what Halperin-Levy did.
No,
right?
no. So there's an approach to all of these Lofton states in terms of Chern-Simons theories.
Okay.
You then do a particle-vortex duality of that, which screws with the Chern-Simons quantization. That gives these theories that Zhang, Hansen, and Kivelson originally wrote. So the original theories, I think, are not the correct effective field theories. Because they don't have the right quantization of Chern-Simons.
Anyway, Halperin-Levy are doing this mean field.
And Halperin-Levy fits within that dual picture.
And then they do RPA fluctuation about that mean field.
But nonetheless, it's true that they can predict many of the right quantities.
Sure, and so can the wave function. So it's not.
True, you can get it from this.
I mean, certainly he can predict things about the. Yeah, he can get some numbers.
See, then maybe I'm wrong. Maybe he can do as much with this as HR.
Yeah, but this is as good a wave function as any of his other wave functions, right? Or no?
Yeah, but what do you do with it? That's the question. How do I predict susceptibility to this?
That offer
To work with.
to work with.
Yeah.
How
How do you calculate a number?
Yeah, how am I going to compute
on the other
the
hand,
specific heat of this
But this RPA expansion, it's not clear what the next order term is going to be, and then why should I trust that? I've never understood actually.
Maybe sophisticated. Looks
No,
hard.
this is sort of an old angst because I learned this in grad school from Reed, and of course he talked about it as if it was the gospel truth, but I never could understand it very much. So, why is it more sophisticated or not?
Can I just go back to asking another question? If I took, and maybe this has been asked many times, sorry, if I take the composite fermion picture literally, so I have one electron and two fluxes, one electron and two fluxes, and I exchange them.
This is the right way.
Okay, this is the
Not
right.
just one electron moving in.
Yeah, it's one electron and two fluxes literally.
Yeah.
And I exchange, and the statistics is still that of
an electron,
electrons,
absolutely.
right?
Yeah. It's called composite fermion. Fermion means that the object itself is still
It is a fermion. Okay.
Yes.
But if I now, I don't know anything about how the mapping was right there, but if I take a electron coupled to this Chern-Simons theory you were saying of level half, then I have to think about the Chern-Simons field and so on. And now I exchange two of these objects.
Still
is it still
must have said, yeah. So
Okay.
see if we can work it out.
I can do that. I was wondering whether
Half
that's
B is equal to Q. That's the.
you're still getting science.
No, I thought obviously.
Yeah, that's what I'm
So
confused about.
this is Gauss's law and Chern-Simons theory coupled to electrons, which means that B is equal to 2Q. That's the statement. The things that I call vortices in this lecture become the flux for some emergent gauge in the atmosphere. But by the way, if you read the original papers, there's some confusion about whether the flux is the magnetic field itself, which just makes no sense. It's usually called the field. Because it's some emergent. So now what I have is each object in the Chern-Simons theory is an electron with 2 units of flux.
Mm-hmm. And Q is 1.
And Q is 1. And I think this is exactly what's needed for the object to give that.
But this is what I'm not understanding. Now let me take one of these around here.
Yes.
And compute the net phase that I get when I do this. How should I count that? I'm taking the electron around the vortex, but I'm also taking the vortex around the electron.
This is a famously subtle factor of 2.
Yeah, exactly. It sounds like it doesn't work like factor.
But the naive factor of 2 is wrong.
Because the other one works.
No, this is a precise answer.
It's a famously subtle issue, and it's got a footnote in Z's book. So the issue is that, let me see if I can get this right. You take this object around this object, and the phase works.
No, I don't even understand that. See, taking that object on that object, the electron will pick up 4 pi.
Yes.
Okay? And plus whatever it picks up because it goes around an electron.
Let's say nothing.
Nothing. Oh my
No,
God.
that's
Very far away, no? Because it's very far
So
away.
exchange is better than going all around.
Yeah, okay.
Exchange is better than going all around.
If you want to think of every one of these objects giving a phase from every one of these objects, you get the wrong answer by a factor of 2.
That's exactly what I asked.
Yes. And the right way to do it, one right way to do it is to go back to the original Chern-Simons theory.
And just do it in Chern-Simons.
Do it in Chern-Simons rather than with this, and then you get the right answer. And
So how do you do it in the what does that mean?
it means that you write down field equations with delta function sources.
Yeah.
And then you vary the positions of those sources.
Yes, exactly. But it's exactly what this
That's the point.
Because we write it down the phase picked up by the wave function as you go around something else, and that wave function will not be a wave function; it will just be a wave function of the electron.
Yeah.
It'll be like say if you're getting a Chern-Simons field.
Sorry, which calculation the calculation we did before. I still don't understand the issue because it's a composite fermion and it's just moving in whatever it's moving in. You don't get to say whether they're electrons or composite fermions because it's just a wave function. Right, so I can tell you what I'm moving, but I can't. I don't have to give a name to the objects inside because it's just a wave function. I can vary phase for that wave function. But this is different. Right now, I've said there are 2 objects of a particular kind and I want to exchange them with no different.
So the actual calculation says put a delta function source for this fake magnetic field for the flux for the
2 delta function sources in the Lagrangian for the Chern-Simons.
okay for this little b.
Yes.
Yeah. Okay.
Yeah. And now exchange them.
Yeah.
I know I'm going to say something wrong, but I think it's something like the background fields turn on when you exchange them. The electric fields turn on and give some extra contribution to this. I wrote something in my notes about this.
I mean, even in sort of, I don't know, QED or whatever, it's not obvious that if you have a composite dion and you exchange, I mean, is it obvious that if you have a dion and you exchange 2 of them, you can think of it as the constituents being exchanged? I mean, the diamond is a little different, no? Because is it obvious that because the effective charge,
pluses and minuses, I think it's fine.
I mean, here it's something similar, right? We have let's literally ask the question. Never mind if it's correct. So we have a vortex of whatever charge 2 and an electron together at one location and another like that, and we exchange them. What's the phase we get?
Yes.
Right? This should have a clear answer.
And it's not the answer you get by thinking that every one of these objects.
And I don't see right away why it had to be as if it were individual.
So what is the right answer? The right answer is when I exchange 2 of them, I get a minus.
Yes.
Right?
Does anyone have a copy of my notes with the Chern-Simons section in it? No, I didn't bring it.
But the electron moving in the field caused by the second particle. The field caused by the second particle is the field caused by traveling. It will just be like the electron moving in the magnetic field of the other guy. That's how the Feynman diagram will work. Suppose you just do a tree-level Feynman diagram. That you'll interpret this as the first guy, that the photon coming, that's the field produced by the first guy, and this guy going down. I think that's how it works.
Okay, so I can tell you what I did in route to the lecture notes. Can I just check if it's the same issue? So I said here, there's a famously annoying factor of 2. The charge q of the first particle moves around the flux phi of the second.
Yeah.
We pick up a phase e to the I q phi.
Yeah.
But you might think that the flux phi of the first particle also moved around the charge q of the second, so surely this should give another factor of e to the I q. And it doesn't. Okay, so why doesn't it? Okay, so here I went through and did the calculation properly of the Chern-Simons theory. You put in these delta function sources. You then move them and you solve the Chern-Simons equations, the time-dependent Chern-Simons equations. And then you compute the Wilson line for what? For A, which is the background Chern-Simons. Okay, you do the calculation.
It comes out like that.
But that factor 2 is not there.
Effective Arnav-Bohm phase and scattering instrument. I think.
Yeah, okay, that's a good way to ask.
Yeah, and of course we don't. I think you can imagine it coming from Feynman. Okay, let's do the tree level. The tree level Feynman diagram can be interpreted classically as this particle moving in the field caused by the second particle. Okay. So you don't see the second effect at all. It's just one guy moving in the field of the first, which would give it with a factor of 1.
The field being just due to the charge, not the...
Yeah, I mean you could say either way. This guy moving in the field of that, or that guy moving in the field of this, but you won't see both.
Are you saying that?
Now I
Which is what you do in the calculation with the wave function.
Exactly. It's what you were saying.
Yeah.
Okay, but this is a manifestation of the following much simpler situation that if you want to compute the potential energy between 2 charges, right, then you can work it out by saying, let me calculate the field produced by one first. There's a very important half. And there are many ways to do it, but another way to do it is to compute the net electric field generated by all charges and then include the rho A term and then it cancels. Or you don't include the net electric field and just do it like that and get the same answer. That's some baby version of this.
Yeah.
Okay. Now I understand why it's such. Okay, I see. Okay, I see. Alright, okay, fine.
But you are continuing with, so you got to the point in the derivation where you do this.
Yeah.
No, there. You have these 2 tubes attached.
Oh, yeah.
Yeah. And then the next step in the field theory way of thinking is?
In the field...
Is to smear those tubes out, right?
No, you just
No?
You solve the
No, not for the Weinglass calculation.
Yeah,
but for doing calculations about the Fermi liquid.
Oh, I don't know.
Oh.
I'm going to stop here and direct you to horrible Lee Halperin reading.
Yeah, because my impression is the next step they do in your picture is smear out those tubes.
Oh, that's your mean field.
Yeah, then That's also a very violent thing. Right?
Yeah, certainly.
Can I ask a historical question? Is the paper by Witten, Halperin and Wilczek after
I don't know.
It's before.
It's before.
It's substantially before. This wasn't until 93 or 94.
I think historically, Jayan wrote the wave functions down, and they, as you said, it was controversial.
I don't know if Jane realized.
I mean, he wrote the whole composite fermionic theory down, right? He said, I will attach even
this
for the particular case.
Peter Simon's theory, Witten, Halperin.
Okay, so one, I don't know whether there's a
Who
particular
was
note about
believed
it.
this was. I suspect Reed, actually. Reed has some papers that predate HLR.
Yes, yes,
And I
that's
suspect he
right.
first realized this was correct.
Yeah, it's
But I'm not sure.
Because they have a mean field in that.
Is that right?
And uncharacteristically for Witten, it's a totally uncontrolled mean field.
I think there's very little else you can do with this problem, perhaps. Right?
Okay, this was all I wanted to say about composite fermions. In the next lecture, we'll do non-abelian states. This Fermi surface is actually going to arise in an interesting way. Because if you have a Fermi surface, the obvious thing that can happen is it can have a superconducting state. So we're going to see what the interpretation of that is in the next subject. Again, I won't do many details for that, but everything else will be. Next lecture, more rigorous than this.
The next one's Friday.